you. So thank you for coming to attend my PhD defense. Today I present you my work entitled Processing Geometric Models of Assemblies to enrich and restructure them with functional information. This work is done in the frame of Roma project, where the aim is to accelerate the product development process through the reduction of time necessary for numeric simulations. As the title implies, our starting point is the geometric model of assemblies, collectively referred to as the digital mockup or DMU. So what is a DMU? Indeed, it's a set of 3D objects that are put up or assembled together in a spatial configurations. Now, is it only about geometry in the DMU? The answer is no. Actually, at least in a DMU, we have the construction tree, which reflects the steps through which the product went through the design process. It also may contain other textual information that gets pretty close to functionality. However, this information is proven to be unreliable. Now, what do we expect from the DMU? The DMU is meant for manufacturing. However, in the frame of Roma project, we expected to provide as well basis for simulation models. Now, simulation is the study of a given phenomenon under certain functional circumstances to assess compliance of a model to the initial requirements. Now, thanks to the digital computation advent, nowadays, old physical prototypes have been replaced by numeric simulation. The latter have the advantage of being timely and repeatable as many times as needed. In the example shown here, it is a substructure of an aircraft, as a user study used in the Roma project, referred to as the root joint. It takes about 15 minutes to run simulation calculation on this model. However, it takes up to 5 man-days in order to prepare this model for simulation. Now, this timely and lengthy process actually introduces a bottleneck to the product development process and raises the question about how to reduce this time. Now, before answering this question, we ask ourselves, why do we at all talk about preparation, and why are they necessary? Indeed, to enable timely calculation, certain simplifying hypotheses must be made once the simulation objectives are set. Now, the aim here is to represent components in a simple way while staying as faithful as possible to reality. Now, this would mean that CAD models are different from simulation models, and shape transformation are indeed necessary. Now, transformation methods, automated transformation methods do exist. However, and no matter whether automated or manual, those transformations are information intensive. This is because objectives of simulation, they refer to functional subsets of the model, such as here in this example. Before I can simplify whatever, I need to spot bolted joints, which is a functional subset. Another reason is the fact that hypotheses themselves, simulation hypotheses, they refer to geometric object and particular geometric zones, such as in this example, I need to spot lacquer nuts, and the simplification method then would dictate that I remove the lacquer nuts, then I detect threaded links, for instance, to join objects as both sides. So I do need those functional information in order to prepare my CAD model. Now, this would mean that before any geometric preparation can be accelerated or fully automated, the geometric model represented by the DMU needs to be enriched with functional knowledge. Now, to this end, it also would need to be restructured and reorganized to enable the reception of such a knowledge. Now, this sets our objective to enrich DMU with functional knowledge needed by geometric preprocessing for finite element analysis purposes. Now, this must happen in the context of mainstream industrial practices, taking into account commonplace representation conventions made in this domain. The starting point to our approach, as mentioned earlier, is the pure geometry of the GMU. Then we extract a geometric interaction between components, and we try to give them an initial interpretation, functional interpretation based on pure geometry. Then we assess those interpretations through a qualitative method against mechanical behavior. Finally, we complete the functional picture by gathering bits and pieces of information into one coherent knowledge base. Now, then we end up with the same GMU, now restructured and enriched with functional knowledge. In the rest of this presentation, I will go into more details of each of the three stages of our method, or proposed method. First, let me introduce you a central paradigm to our research, that is the relationship between form and function. So functionality can be seen as what designers and engineers had in mind when they created their model. Now, there is the relationship between function and structure has been emphasized through the literature. However, functionally relevant structure is still missing in the GMU. Nonetheless, its embodiment, the form, is available, and it provides the first clue towards a functionally significant structure. Now, efforts have been paid to connect form to function in a top-down approaches that use what is referred to, that enhance and boost the design activity, and use what is referred to as a goal achievement path. Now, these methods remarkably applied behavior in order to make that connection. Now, in our method, it's a bottom-up method that aims at making the same connection, but now the other way around, from form to function. So in this endeavor, certain challenges and obstacles have been met, the first of which is actually the difference between real and digital shape. This is a direct result of conventional and industrial convention, representation conventions. In this example, we see a simple screw and nut, both bearing a threaded link. Now, in the real shape, the threaded link is represented as a helical cut. In a DMU, in the vast majority of industrial models, this is simplified as simple cylinders. Now, these representations are not unique. Conventions may differ. So cylinders at both sides, they have either equal diameters or not, depending on the convention. That would mean that the form-function relationship in the DMU is indeterministic. Now, another challenge is the need of restructuring. The DMU, the way it is now, is not ready yet to accommodate functional information. In order to enrich the DMU for finite element analysis purposes, enrichment should happen at three levels. The first level is the functional interface level, where we need to tell that a certain interaction between two components is, for instance, a threaded link or a planar contact. Now, to do that, we need to isolate this geometric entity, something that we do not yet have in the GNU. So we need geometric restructuring for at the interface level. Now, for components, we need of course, to explain them functionally. However, components are isolated, are standalone objects in the GNU. So no particular restructuring is needed for at this stage. However, components themselves are restructured to allow enrichment at the interface level. Now, finally, at the functional group level, we need to group components according to a common functionality. This would imply the reorganization of the GNU to this end. Now, this will lead us to the first part of our proposed method, that is the form analysis. Now, before I go further into this part, we ask ourselves this question: is geometry a valid entry point? To answer this question, we observe that a single component cannot deliver much functionality on its own. Functionality actually happens at the interaction level between different components. Now, in a mechanical engineering context, this functional interaction has a geometric nature. Literature actually provided top-down, again, goal achievement methods that built on this functional interaction paradigm. Now, in our approach, and since function stems at the geometric interaction level for a mechanical component, geometric interactions between components must be analyzed first in a bottom-up approach that is ours in order to obtain any functionality. Now, this proves our entry point to be valid, which is geometry. Now, to seize this geometric interaction between components, we define a conceptual entity that we refer to as the conventional interface. Now, even though it is identified, conventional interfaces are identified by the geometric interaction, they can be assigned, and they will be assigned, other functional and physical properties, as we will see shortly. Now, conventional interfaces are classified according to this intrinsic geometric nature. So first, we have context between two components. When two components touch each other, leaving no volume intersection. Interferences, when two components actually penetrate each other, leaving a common volume. And clearances, when surfaces of two components keep a certain distance between each other, is referred to as the plane. Now, the first observation that we make is the irrealistic nature of interferences. Objects, in reality, they do not interfere. So this is a purely conventional interface. It's a pure convention, interferences in the GMU. Another observation is that clearances, to detect clearances, we need a parameter that is the plane. Now, planes have functional meaning. So that dependency of clearances on functionality prevents us from exploiting clearances as for now. So in an attempt to functionally explain conventional interfaces, we define the functional interface that capture intercomponent interactions that fulfills or participate in the fulfillment of a set of functions. Now again, we observe that one particular geometric configuration captured by a conventional interface can be interpreted in more than one functional way captured by the functional interface. So one CI can relate to more than one FIs. This is a direct result of the indeterministic relationship between shape and function in the GMU. Now, if we refer to geometric surfaces now at both sides of a functional interface as functional surfaces, we also observe that in a GMU, functional surfaces are mainly in the vast majority of industrial practices are canonical surfaces, that is, planes, tori, cylinders, spheres, and cones. This is because even when non-canonical surfaces convey a functional meaning, in this example, the threaded link and the involute profile in screws and gears, even when they do convey a functional meaning, they are, those profile and surfaces, they are machined independently from the CAD model. So the CAD model is actually simplified in these cases using, again, canonical surfaces. Now this allows us to safely state that as long as functionality is concerned, only canonical interaction between canonical surfaces is of interest to our study. Now this allows us to define a simple yet efficient geometry detection method, but before any detection can be made, we have to obtain a unique geometric representation of the model that we refer to as the maximum edges and surfaces representation. Now once this is done, we go through a 3-level filtering to detect the geometric interaction that starts by a simple bounding boxes check to eliminate obvious negatives. Now, canonical surfaces of neighboring components according to the bounding box check are then compared pairwise using their simple geometric attributes, and candidate of an interaction is finally reported to a Boolean operator check, final check, that allows us to eliminate false positives and to precisely detect the interaction zone. Now it's worth mentioning that in the frame of Roman project, other works has been done to precisely and efficiently detect certain geometric configuration. Now, once a conventional interface is detected, it links actually two components of the GMU. Now, this defines certain topology on components of the GMU that we capture in the conventional interface graph. Now, this graph has components as nodes and conventional interfaces as edges, and it replaces the construction tree with a more functionally relevant graph-like structure. This defines the first step towards a DMU structure. Now, to show some results at this stage, we take the example of a centrifugal pump that we used, and it would take to generate the conventional interface graph using mere Boolean operators. It will take about 8 minutes, while using our 3-level approach, it would take about 150 milliseconds to generate a 100-edge graph. Now, another more elaborate example is the root joint that we've seen at the beginning of this presentation, and it would take, using our 3-level filtering, less than 200 milliseconds to generate a more complicated graph. Now, up till now, no functionality has been mentioned in my presentation, although our ultimate objective is to bind form to function. Now, if we try to interpret our geometry functionally at this level, we would say that cylindric interference can be interpreted as a threaded link, which is true, but it's only part of the truth, because the same geometric convention, the same geometric configuration can also represent spline link that I show in this example. It's a kinematic link that transmits rotation while still allowing translation. This link is also commonly represented by a simplified in GMUs by a simple cylindric interference. So the connection between form and function is ambiguous. So we need more information to clarify this, and we will borrow context as we'll show shortly. But as for now, we are interested on giving all possible functional interpretation to a certain geometric configuration. To this end, we organized our geometric and functional knowledge at the interface level in what we refer to as conventional interface taxonomy and functional interface taxonomy. Now, interpretation then happens at the deep level of those taxonomies, defining a dictionary that binds each conventional interface with potentially multiple functional interfaces. Now, this puts a structural frame on our geometric and functional knowledge. So, to position ourselves with respect to the objective set, we have so far bridged actually the connection at the interface level between conventional interfaces and functional interfaces. However, this connection is still ambiguous, as we've seen. Multiple functional interfaces are potentially linked to one conventional interface. Now, we started by restructuring the GMU to enable the enrichment at the functional group level. So, to clarify this ambiguity, we borrow
context, as I mentioned before, and this is the subject of my next part, which is a qualitative behavioral study. The idea here and the question that we ask is, can behavior that is used throughout the literature to bind, to make the link function to form, be applied here to mend the ambiguous, yet ambiguous link between form to function? So to illustrate this possibility, we come back to the example of a cylindrical interference, and we know that this can be interpretation. The interpretation of threaded link is valid both from a geometric and behavioral standpoint. Now the alternative, which is the spline link, even though valid from a geometric standpoint, it is not from a mechanical behavior point of view. That would mean that forces actually cannot be balanced using this interpretation. Now this sets our short-term objective of this part, which is to use such behavioral judgment to narrow down the number of functional interpretation per conventional interface. To this end, we introduce the concept of reference states, each defining what a valid behavior is. And the idea then shifts, the goal shifts to eliminating functional interpretations that violate one or more reference states. Now, before going into details of each of our defined reference states, we define a set of hypotheses, global hypotheses. We first assume our components to be rigid bodies and the deformation to be negligible. We also assume the product to be an energy conservative system that our contacts are friction-free. We also only consider mechanical interactions, that physical interactions with components only go through conventional interfaces, which are geometric interfaces. Now, the first reference state then comes to regard the product at rest, and it asserts that components of a product hold in place. This can be formalized using mechanical equilibrium equations, and this statement actually casts a physical dimension on pure geometry. Now we know that a system of external forces and external moment applied on a rigid body can be represented by a force vector and a moment vector, that is a wrench screw. Now assigning a wrench screw to each conventional interface based on a given functional interface, functional interpretation or functional interface allows us to state mechanical equilibrium equations as follows. The sum of all wrench screws over all conventional interfaces of a component equals 0. Now the problem is we do not have those quantities in the DMU. Force and moment are not available in the DMU. So we need to represent those quantities and those measures in a qualitative way. We borrow this qualitative representation from interval arithmetics, and we define our qualitative values as intervals, as real intervals, each representing how force or moment should propagate according to a given direction. Now, once it's done, we also define addition and multiplication using, again, the interval arithmetics theory. Now, the idea is to iterate the DMU components as the nodes of the conventional interface graph, and for each component to assess the compliance of this component with reference state 1, and eliminate functional interfaces now that do not abide by this reference state. So we pick our component heuristically. Each time we pick a component heuristically. Now we use heuristics to enable the fast conversions of our algorithm. Once a component is picked, in this case the red component C, we browse all possible solutions of this given component. In this case, this component has two interfaces, one that can only interpret it as planar support, the other can interpret it either as a threaded link or as a spline link. Now this makes the total number of solution sums up to 2. And we browse each solution, and each time, say for the threaded link and planar support solution, we borrow range screws from the functional interface taxonomy. Now, and we sum those range screws. In the way, we would need coordinate alignment and point of application change. We use integral arithmetic to do summation and production, and we end up with a sum range screw. Now, the sum range screw, all of its components actually contains zero. So this is a nullable qualitative value, and it is an acceptable solution. Now, the other alternative, which is the solution of a spline link and a planar support, however, it has a strictly negative qualitative value that doesn't contain 0, and this makes this solution rejected. That would mean that the spline link is a not acceptable functional interface, and it is then dropped from the interpretation. Now, there's nothing more to do at component C because all its interfaces has been functionally determined. One functional interface per conventional interface. So the component C is then closed, and we move on to the next component using our heuristics, and so on. Now this defines a first level of filtering that eliminates a considerable amount of functional interfaces. However, ambiguity still remains because of conventional interfaces that still have multiple statically valid functional interfaces. To this end, reference state 2 provides the necessary criterion to select the appropriate functional interfaces when multiple static solutions coexist. Now, reference state 2 consider the product as in operation. It asserts that all statically indeterminate solutions must be functionally justified, otherwise they must be eliminated. Now, the elimination of non-functional statically indeterminate solution would lead to one functional interface per conventional interface. This provides the second and last filtering at the interface level and leads to remove the ambiguity at this level. Now, as mentioned earlier, another required enrichment for for finite element analysis purposes is enrichment as at the functional group level. Now, a functional group is a set of components that participate to the fulfillment of a coherent set of functions. Each functional group is labeled by means of a functional cluster that designates the set of functions it satisfies. An example is a bolted junction that we saw earlier that designates a set of components that satisfy tightening by means of a threaded link. Now, a threaded link is an internal force generator, and bolted junctions are characterized by internal loads cycles. This leads us to reference state 3 that states that an internal load generated by a load generator propagates inside the product in cyclic paths. Now, this raises the question as how to detect internal load cycles. To answer this question, we define a force propagation graph per each force propagation direction. Now, one thing that we know about force propagation graphs is that are subgraphs of conventional interface graph. This is because force can only propagate through conventional interfaces according to the only mechanical interaction hypothesis. Now, this puts an upper limit on the number of force propagation graphs. Now, for each force propagation dictated by an internal load generator, we start by eliminating functional interfaces that would lead to a non-functional, statically indeterminate configuration. Then we project the conventional interface graph onto the chosen direction, leading to the force propagation graph or graphs. Now the detection of bolted junctions now boils down to the query of cyclic paths on these graphs, and each cycle is then labeled as a functional group as a bolted junction. Now, so far, and using a qualitative behavioral study, we have eliminated ambiguity of functional knowledge at the interface level. We also acquired new functional knowledge at the functional group level to situate ourselves with respect to objectives. The bridge is completely bound between form and function at two different levels: interface and functional group. Now this leads us to the last part of our contribution, which is the rule-based inference. And the idea here is to use this unambiguous knowledge that we acquire at both levels to deduce new knowledge at the component level. So to this end, we define the functional designation, which is a denomination that uniquely identifies a component from a functional point of view. Now, we observe that functional designations are not simple textual annotations. They actually relate the components with functionality at other levels, such as the interface and the functional group level, as we will see shortly. Now, the first observation is that functionality of a component cannot be told by looking at the component itself. We need to know the functional interfaces of the component and the functional group that it participates to. Another important observation is the dynamic nature of such knowledge about functional designation. Actually, the set of functional designations that we may define and may address depends on the underlying domain of discourse, such as aeronautics industry or automotive industry. So we need this knowledge, however, can be represented and structured in a hierarchical structure again, which we refer to as the functional designation taxonomy. We need to represent this knowledge formally, yet in a dynamic and adaptive manner. So far we have been collecting knowledge. Now we need to represent this knowledge and we need to process this knowledge. To answer this question about how to do that, we take a look at what literature provides in this regard. A common approach is the knowledge-based engineering approach that emphasizes reuse by making knowledge available throughout the design activity. Now, one drawback is that KBE systems adapt to CAD systems and do not try to change them. This would mean that technological and functional information are kept disconnected from their geometric counterparts. This is because geometry is kept untouched. Another inconvenience is the use of procedural and object-oriented approach that disallow the use of dynamic rules, and again the use of native languages that hinder knowledge sharing, the initial motivation behind KBE. Now, another alternative is ontologies. Ontologies are have well-defined semantics based on the semantic web paradigm. They provide a generic tool for cross-domain knowledge representation. They have been intensively used to represent functional knowledge. However, little has been done in this domain as far as we know in terms of reasoning. Reasoning didn't go beyond basic consistency checks and certain reduction of some kinematic properties. Now, in our approach, however, we need more than consistency checks in our reasoning. An example rule that we need to reason upon is the definition, the simplified now definition of a cap screw, which states that a cap screw is a component that has a threaded link and a planar support and that participates to a bolted junction. Now, an important notice here is that this rule actually emphasizes the tight relationship between component function and the functionality at its interface and functional group level. This rule can be represented using first order logic, using those formula. Now, however, first order logic is proven to be undecidable. The same rule can be represented using description logic, which is a decidable fragment of first order logic. Now, description logic has also the advantage, besides being decidable, has also the advantage of having an ontology logic in its back, its OLGL, which is an ontology logic that totally supports DL reasoning. Another important advantage is the existence of industrial and open source reasoners that implement algorithms, efficient algorithms to do DL reasoning. Now, once the choice is made of how to represent and process knowledge, which is ontologies and DL, we define our domain ontology, the Roma ontology, using OLGL. And then, for each DMU, model knowledge is instantiated against concepts of this ontology, and instances of this domain knowledge are related to their respective geometric entities in the DMU. Now, to give an idea about how reasoning is done, this scheme shows this process, the process in general. So the Roma ontology is defined here. Then it is submitted to the reasoner using DIG protocol to consist the T-box of the knowledge base. Now, next, the previously generated conventional interface graph and functionally enriched conventional interface graph is translated into facts, and those facts themselves are submitted to the reasoner as well to consist its A-box, now the A-box of the knowledge base. And then finally, the reasoner is inquired about function designations, and matching is done. In this particular case, we can infer that component D is a cap screw. A matching is done between instances and rules. Now, at this stage, functional units, which are components, are enriched with functional knowledge down to the interface level after they have been geometrically restructured to this end. Now, to show some results, we take the centrifugal pump again, where 6 different function designations have been successfully recognized. The example of the root joint as well, cap screws, nuts, and locker nuts has been successfully detected in this example. To position ourselves again, objectives have been met, and the information gap has been completely bridged between form and functionality, producing a reliable functional knowledge base about the assembly that connects concrete structure and geometry, that connects to concrete structure and geometrical elements. Now, a direct application of this approach is what has been done in the frame of Roma, again, in the frame of Roma project by Bosuj et al. It is a highly automated geometric pre-processing method for finite elements simulation purposes. It is based on template matching. For instance, a bolted junction is matched with a template. Now, this method feeds on our proposed approach. So the bolted junctions are recognized thanks to their functional annotation, functional clusters. Then once a bolted junction is detected, lacquer nuts is spotted using their functional designations and removed according to the template. Once this is done, again, interfaces of loose fit, well, threaded links first. Threaded links dictate that objects at both sides must be joined, must be merged, as the examples show. Then finally, interfaces, cylindrical contacts between components that is interpreted as loose fits, dictate where to create domain decompositions. Now, this will give us finally an adequate simulation model. This collaboration reduced the time necessary for preparation from 5 man-days to only 1 hour. Now, in conclusion, the geometric structure of the DMU has been geometrically restructured. Interaction between components are isolated. Components now bear imprints of those interactions thanks to their conventional interfaces. Those interactions have been functionally described and explained using one functional interface per conventional interface. The DMU as well has been restructured functionally. We defined a new functionally significant graph structure thanks to the conventional interface graph, and then groups in the DMU has been regrouped in functional subsets that is referred to as functional and labeled by their functional clusters. Now, to this end, we used a qualitative behavioral assessment of functionality in a mechanical context. We defined reference states to do this job. Now, we also applied a rule-based inference to complete the functional picture of the GMU, building an ontology of functional designations. Now, in perspectives, other applications rather than finite element analysis purposes can be considered, such as virtual and augmented reality and assembly and disassembly planning, where newly acquired functional and kinematic properties can be applied to this end. Now, future works and direction include to take into consideration geometric repetitive geometric patterns and symmetry in order to enhance the execution time by avoiding redundant reasoning. Another possibility is the implementation of reference states that take into account the violation of the global hypothesis. We made a set of global hypotheses. Now, these global hypotheses, if violated, we need other reference states to take into account this violation, such as deformable objects and contact with friction. Finally, the extension of our ontology by adding new rules to detect new functional designations. Thank you for listening.